We're just beginning to examine what happens when the geostrophic balance is broken, that is, when the Coriolis acceleration is no longer able to be balanced by the horizontal pressure gradients. In this video, we're going to examine some consequences of viscous boundary layers in rotating flows. We'll see how viscosity near a boundary operates to slow a fluid and thus reduce its velocity-dependent accelerations, subsequently breaking this bulk dynamical balance. We'll begin by considering a cup of tea that is rotating at a rate omega. Exactly why tea, we'll come back to in a moment. Imagine the tea is moving with the cup, a state that's referred to as solid body rotation, so that in our inertial frame, the velocity u is simply a function of radius, omega r. In the cup's reference frame, the tea is at rest. Being at rest means there is a balance of forces within the tea. Having u equal to 0 means there is 0 Coriolis accelerations, however there are centripetal accelerations. The centripetal acceleration experienced by the tea, omega cross r, or omega squared times the radius, is necessarily balanced by the only other force available to the system, a pressure gradient, grab p on rho. Given that the centripetal acceleration is a function of radius only and rho is uniform, we can write grad p on rho as simply the radial pressure gradient, 1 on rho dp by dr. So the centripetal acceleration omega squared r is balanced by the radial pressure gradient, 1 on rho dp by dr. This equation can be integrated in the radial direction from a radius of 0 to r, giving the pressure difference between 0 and r as half times density times omega squared and radius squared. Consider the T to be in hydrostatic balance, so that the pressure at the point Rz is just the density times gravity times the difference between the free surface height at R and Z. This is substituted into the pressure integral to return the difference in height between a radius of 0 and a radius of r as equal to omega squared r squared on 2 times gravity. That is, the free surface is parabolic in r. So, for solid body rotation, the radially outward centripetal acceleration must be balanced by a radially inward pressure gradient, which is achieved by the T free surface adopting a parabolic shape. Now, imagine that we are in this balanced state of solid body rotation, and we slightly slow the rotation of the cup to omega s, so that the T is now spinning faster than the cup. Initially, in our inertial frame, the T remains at u equals omega r, while in the cup's frame, the T velocity is now delta omega r. The centripetal acceleration experienced by the T in the interior remains balanced by the radial pressure gradient. However, at the base, next to the bottom boundary, in the viscous boundary layer, the velocity of the T has slowed to u equals omega sr, reducing the outward centripetal acceleration it experiences to omega s squared r. This no longer balances the inwards radial pressure gradient, so the T here flows inwards. Over time, all of the T in the interior flushes through this bottom boundary layer and slows to the new solid body rotation of omega s. This is referred to as spin down. It is this process that leads to tea leaves collecting in a central clump at the bottom of a teacup. The centripetal accelerations induced by the spoon stirring the tea leads to a radial pressure gradient that's oriented inwards, and this pressure gradient persists after the spoon is removed. Any location where the centripetal acceleration decreases, such as the base, will exhibit an inwards flow. The tea leaves themselves are ever so slightly denser than the tea, meaning that once they collect in the central clump, they are too heavy to continue flowing with the spinning down fluid. The combination of their density and the unbalanced inward pressure gradients in the viscous boundary layer leads to the convergence of tea leaves here. In the case that the rotation of the cup has the opposite perturbation, the sense of the resulting circulation is reversed. T near the bottom boundary accelerates, increasing its centripetal acceleration, which is no longer balanced by the radial gradients in hydrostatic pressure, driving a radially outward flow in the bottom layer. Again, this continues until all of the fluid in the interior is flushed through this bottom layer, where it is accelerated to the new cup rotation rate. Now, this simple example that we have considered here is two-dimensional and rather idealized. As we are about to discover, reality can be much more complicated. Here we have seen that viscosity, in this case, has broken the bulk dynamical balance between the centripetal acceleration and the hydrostatic pressure. What we do next is to take this process and apply it to the geostrophic balance.